it is something 10 megawatt. And referring to this, now we have like there are different techniques or the methods that have been applied, and each one of them is about how we can monitor the power grid, and this is based on the synchrophasors informations. So just to give you, I have just one slide here to what is synchrophasors. So you can see we have a signal which is which is in fact as a time domain. So we can represent them as a phasor information. So in terms of the voltage, here as shown is the magnitude and the angle associated with this time varying oscillator singular. And with the, so with these phasor informations, they are it could be like at one of the substations, and then its clock being synchronized with the GPS satellite. We can have the synchronized time signal here through the in the form of single phasors here. So we there had been in the market like some devices which has been developed, and that could be. I hope you are very well aware of those devices. We call them as phasor measurement units here. And that's with those devices, it is possible to have the signals and their fact the signals as in the real-time monitoring for the power grid information. In fact, so this is how it looks like. Most of the PMOs on their installations. So these PMOs they measure the bus voltage or the phase of the sequence, and all they can be in all the three phase line currents, and then from different substations. Uh, Here we have the slide that shows what could be the different applications, how the phase informations could be useful actually. And you can see that it can be like, in general, this is referred here. So it could be like a system, how we can improve the system reliability and have increased grid asset utilization, and then the further improve the efficiency, power system efficiency, and then increase organizational efficiency. And these are some of the challenges they are referred down. So it could be wide area visualization, frequency stability, monitoring, oscillation detection, and so on. And also you can see the state estimation, post-event analysis out of the data that has been collected through the phasor data concentrator and so on. And also we have like the it could be like developing a model, theoretical model based on the experiment signals actually after the that could also be possible here. Now, this is the first project that I refer here, and so that's we have some of the wide area monitoring system projects, and the first project is the Stronger projects, and it was led by Setal. It was long, you can say 1 decade back, and it was funded by Northern, and I refer to some of the results out of this project. So, as a part of the Sustainable Energy Systems 2050, it was funded and on Nordic Energy Research, and also funded by the Nordic DSOs and DSOs. So, as a objectives in this project was to develop some tools for better operation and control of the power grid, and also have some innovative applications that could be applied in the reliable operation and control of the Nordic power grid. So it's like Nordic power grid, though now it is well connected to the rest of the Europe, but as a whole, to mention here, the Nordic power grid, it is forms interconnection between Norway, Sweden, Finland, And now, since I said it is now well connected to the rest of the European, so we also have that means power flow or the exchange of the power flow basically to the rest of the European countries as well. And identify technological gaps and the limitations that could be addressed in the future as a roadmap for smart grid operation and also considering the renewable integration with the existing grid. So in this project, we have a consortium of academia. We have several universities, and then again, some of the so it's like the transmission companies, Statnet. Then this one is the DSO based in Norway. Then it's a transmission company in Sweden and DSO in Sweden and transmission TSO that is based in Finland and landslide that is in Iceland. And these were the country partners here. This motivation for this project was that we had been monitoring some of the scenarios, and then there was a need to have faster and large changes in the operation. That was the trend. We want there was a variability and uncertainty in the grid systems, and then this led to the less predictability. So we have less time to take decisions actually, and thus we wanted to have some tools for the real-time monitoring application. So thus the operators, the grid operators, they wanted to have new tools and which could be as a real-time informations with higher resolution of the signals and also synchronized measurements. They have the need for automatic control and also, of course, to explore new technology or new possibilities that could be out of this project. As I said, so create innovative applications and then as a project goals that will enable operation and control of the Nordic power grid more reliably. So emphasis was how we could have the use of the PMOs, so the WAMs towards the grid development, smart grid development, and also to have a research platform, software and, and hardware labs, and that could be out of the Nordic university clusters. And develop some software interfaces along with the PMO data applications here. So as a part of this project, we had developed some research platforms in the different labs, and that was as a low voltage PMU network. And we had as you can see, this was as an online PMO. It was installed as a low voltage at a low voltage network at different locations here. It refers to the different universities, university partners actually, where we have installed the PMOs. And as a part of this research platform development, we had been able to have data sharing for the real-time PMO data actions, and this is the just refers to the complete conceptual block diagram, and this was implemented in KTH University, and thus with the installation of the PMOs, and then again have you can see each of these locations they had their own PDC here that was an RTU. Uh, then Alto, and then another was NTT, uh, DTU, and Antonio here. So we had from each university partners, we have the PMOs and the PADCs, and there's so that we can have the exchange of the streams, data stream from each other. These PDCs, they were locally allowed data achieving and the real-time access for all the partners, and that's avoided super PDC at a single point here. This is in fact, the image that we had it from one of the test bench in the implementation of the warm pack software application. And this was in this Martyrs lab that was at KTH University. And as a part of this application that could be applied to the TSO, so here it shows that the software that we have developed for the project. So with the actual PMOs at a high voltage network, how they were installed, and then we were able to have the access to the real-time data, and we have the information about the frequency, and then again the phasors, the voltage figures from each of these locations here in real time. Then, as a part of another study, it was like so here it shows an app. So we had and this was a real-time data validator, so being compatible to IEC standard. And all this, we have the graphical user interface that was all developed through the lab here, and different app prototyping functions were included in the application. And here it refers to another visualization tool indicating how from the different locations of the PMOs at the low voltage, and the information about the signals, the frequency, and the voltage amplitude, how it has been able to monitor. And then again, also the mode shape of the phasors here. See, and then again, the bus voltage angle here. Then again, this is another graphical illustration for the application. So you can see we were able to have the selection of the data from which of the lab locations that could be accessed here. And we have the frequency information and the voltage magnitude, and also the voltage angle here for each of these locations. Then, as a part of this project, we also have developed, because we done for the grid operators actually. So that's the tools, visualization tools that could also be uh, adopted for any other devices. So it could be like from a tablet or maybe the phones, and thus the grid operators can have easy access to the real-time informations with the small devices actually, which are we have considered like saying the portable monitoring applications. Yeah, and this set of the tools was developed by Luigi and his team. And then here we have some more results referring to out of this project. So it was monitoring visualization, and then inter-area oscillation assessment out of that, and then force oscillation detection, and then real-time voltage stability assessment, and then real-time PV power voltage stability assessment. So these were out of several work packages included in the project. Yeah. And then there was another Origin project that was the Real Smart project in which I was involved. And this project, again, it was 1 decade back. So it included the consortium of different TSOs, different companies, and of course, some universities. And then I was working at Alto University in this project. And in this project, we were, as a part of Alto University, actually, we had been like working on inter-area power oscillations. So this is the grid map, although we have several interconnections now, and again, it's like not more, all of the lines have been shown here. So due to the interior oscillations, we have the limits on the power flow from Finland to Sweden, and it was for around zero point 0.3 hertz actually. And Then there are some more oscillations, you can say from Norway to Finland that corresponds to zero point 0.8 hertz here. There are, although there are some more in the interior oscillations, but the main focus of my study was on zero point 0.3 mode of oscillations here, wherein you have the oscillation between the generators installed in the south of Finland and south of Sweden. So whenever we have the power flow in this direction, the generators in the south of Finland and the south of Sweden tends to oscillate at zero point 0.3 hertz here. And we have several PMS installed in the grid system here. And then there is another product, Spandex. So it was like the concept of demonstration, development, and implementation of the software applications and interface. And we have the use of the PMOs from the StatNet, TSOs, and then again using the PDCs, and that also included some low resolution signals here, so the SCADA, and then we developed the tools out of this project here. And then they've integrated, that means high resolution signals and the low resolution signals were integrated, and developed some apps for the monitoring here. Then this is another project, Indo-Novel project that was in 2015, in which I was associated from Amanat Allahabad. And then we have settled from Ontario. So from India side, we have the study about oscillation damping and how we can improve the stability. That was through some of the PhD students who worked during this period for 3 or 3.5 years. And then another student who was involved in the protection schemes using the PMS data. And then again, another student was about developing the monitoring solutions for situational awareness. Yeah. So here I have some just included some of the results. So it was about the classification of the events from the NAS PPMA data here. The results I have been included on the slide. So with the events that was from the region 1 and the region 2, how they were classified as the binary. And then here it shows the one of the event, we refer to the event A from the NASP data, and that was the data corresponding to 2014, I suppose. And then the post-event situation as a binary classification, and then we have considered the one of the event, I suppose, as a multi-class between the regions here. And we were able to achieve the classification accuracy around 100%. And then if you want to have some more details about this study, so that is included in some of these references here. Then another study was about the spectral coherency measure between the generator signals. And just to give you the conceptual methodology that we adopted, that's here you can see we have two synchronized signals here, and at this point we have a phase shift of about 180-degree phase shift here at this instant, and thus with this, what we are able to show that what is the oscillating frequency of the corresponding signal here. That is something. And then again in the time domain, how there is a phase information or the phase shift that could be detected or that could be known actually between the signals here. So at this instant of time, you can see that there is a phase shift, and with the methodology that we have developed, we are able to indicate in real time what could be the phase shift between the signals here. So during this time, there was a complete overlap. However, at this instant, there was a phase shift. So with this technique that we had applied on the synthetic signal corresponding to zero point 0.8 hertz mode of oscillations, and then we had applied on data that we can get from the Indian grid. So that was from Agra and Hisar and Agra and Dadri. So that was the actual signal. And then applying some of the techniques actually. So this corresponds to the IMF of the signals here. And then again the spectrograph here. And then here it shows what is the phase relation that we can get out of these two real-time signals here. And this study has been published in this reference here. Similarly, as part of another analysis, it was about how we can obtain a sustained oscillations, and this was applied on the PMU signals from the SR bus, and then we had considered different techniques here, and then this is the oscillogram of the that refers to the power spectral density for the Hisar signal, and with the different this is applying the pre-processing of the signals here, and then here refers to the spectra for different levels here. And then out of those, we have applied BMD technique, and then we were able to indicate the different modes which are present in the actual signals here. Then, as a form of monitoring, then we continued, and you can see that we have from the real-time signals, we can see that at this instant, there is a change in the frequency here, and that corresponds to around 8.7 to 9 hertz something. So this deviating frequency, what we have present in the real-time signals. So we have used this, and then with the techniques that we had. So it was able to say that what is the PST, and then again saying that okay, this will be like the category of oscillation that we have it here. That will be in the category of force oscillations. Yeah. Then this application was developed as considering a time window of and then it was for different measures actually. So here it shows the time window, and then we have considered the signals from different locations here. So this could be like saying running mode shape, and for every 10 to 12 seconds minute, and then 12 to 14 minute, and so on actually. So you can see that how the phasors they are uh, they change their positions actually. The phasor information, they change their uh, placement or the position actually over the time that are present in the signals here. So this one corresponds to we have considered 20-minute data. So this one refers to 0 to 10-minute data, and this one refers to 10 to 20-minute data. So you can see how the phasors, they have changed their positions in the signals that we have. Similarly, this one is another one that corresponds to the mode shape of 0.58 hertz here, and for the same 20-minute time window data. So as in this case, most of the generators, they were, although they were oriented in the same direction, but still they have changed their phase positions here. When we had the study this which we had it here as a real time, but this was applied on as a offline actually. So this the algorithm was tested in real time at CENTEF, and this is the block diagram or illustration to show how the integration was achieved to implement in the real time actually. So WAMPOS, real-time testing of the WAMPOS. So we had the center we had the model in the center for Parala PC, and then it was for one of the student here, and applying this MATLAB based setup. So with these cases, we were able to obtain, we had the simulating and the live streaming of the data. And then again, we get the data from the PDCs in the algorithms, and then the PDCs to the MATLAB, because the main algorithm was actually developed in the MATLAB. So that's how MATLAB was also in use here actually. And to implement this real-time testing, it was actually as a part of the Irrigate project that was in 2019 here. And this is the picture actually that shows how the real-time testing was performed in the lab. And this is another result actually to show. So we had the voltage magnitude live stream, and then is frequency information for the voltage signals. Yeah. This was another, but this was the case of offline results here. That was the real-time signal being stored for the low voltage no, PMO installed in the Nordic grid. And then we also have some application tools that were developed for the testing. So it was referred as software tool chain. So we had like use of as you can see on the slides, nowadays we have several open source softwares actually that are available and that could be applied actually. So this is just the list actually, the name of the some of the open source softwares for the application. And as a part of this study, so we had used Pupo, which was actually C++ based software. And unlike using the commercial software PDCs, we do not receive the real-time streams from the PMS. So in our case, we had the emulation of the PDC behavior, and that according to this IEEE protocol, and we wanted to have some kind of this was actually as a part of the simulator. Uh, and here is the complete flow chart or the algorithm that was developed. So you can see the stored PMOs from the file and converted into the notepad format. And then we had the importing of the files. And then here is refers to the complete development framework application developed. So applying to the IEEE standard, and then again having the streams of different quantities, and then application for control, protection, and monitoring purpose. Actually, here it could be, but although here it shows only for monitoring applications. Yeah. So we had it for its demonstration for testing the PME PDC simulator, mainly people, and then again for oscillation monitoring here, and which was applied on the NASP signal. Then further, these are some more results referring to how the algorithm was tested. So it was like check of the synchronized overlapping, check for the sampling rate, and so on. And here it shows the results, some of the voltage oscillations, yeah, the voltage magnitude oscillations, yeah, that were retrieved in the testing. Then again, there are some more results here. So wide area for oscillation. So it was this is the because the main algorithm that we had developed, it was actually based on the square coherence between the two signals here. And here it shows some of the results for the time delayed window of 30 seconds here. And this result that corresponds to about 13.33 hertz here of for oscillations, and it has been confirmed also from the report that has been published. These studies, what we had, they were actually as a part of several partners, and then so this is so it shows the like how it has been association in different projects. So these are some of the memories. Center of Love, then Man Baden, and even at MNIT Labad, and then at Alto University here. And we have some meeting in Grenoble. And then poster presentation at IEEE Power Tech Conference in Manchester with Settle. And then out of this slide, it is like because this was actually it's a part of the partners or researchers from several organizations, and then it's because some of the discussions that I have included in my slide, they were actually shared by Lugi, and then here we have the different researchers that were involved in the different projects, and then the development basically from the Lugi team. And then there were also like there were some more collaborations from Alto University, then from Fingrid, and then also from Centaf. So some of those studies which had been included in the presentation, they were also from these researchers here. I had a quick, then also it's like we had because some PhD students were involved, and then also the acknowledgements to the funding agency. So we have the DST, then there's a Council of Norway, and then real-time projects, irrigate project, transnational, and then different labs here. And these are some PhD students or the master students. So who had out of this study uh, received some recognitions from that we call it as POSCO Power System Award. I think this was in 2016 and that this was in 2017 here. And then with this, I it very short in my presentation, and then this is the last slide. And if you have anything, let me know. But I think yes, I have, because it was about for 1 hour, so it was like have consider the presentation just for 45 minutes something, and then I left something sometime out of 1 hour for discussion actually. So if you have, then we can discuss here.
Thank you so much, sir, for your nice presentation on wide area monitoring and stability issues, which is explained nicely, both in simulation as well as in real-time applications. So now I will invite some of our this audience to ask some questions related to the presentation.
Sir, good morning. Sir, good morning. This is Rajita here from Odisha. Myself, regarding the technical presentation, and it was very nice, insightful presentation because real-time data it was taken, and there was also simulation studies involved. So I have one question that please so this really heard and when you did this PMU studies for the area situation. So what was the observation point of view that how much the acceptable angle of the deviation which can be actually mentioned within two
I'm sorry to say, actually, as you started with the question, it was too long, actually, and there was. What you say exactly? In short, can you say the question exactly? Because I could not get it. You started with how many something, actually, right? And then what is the exact question, actually?
Sir, am I audible, sir?
Yes, this is now a little bit perfect.
Yes, sir. Yes, sir. So, sir, I wanted to ask that how many degrees, because we are it like we have taken Dadi station and we have taken another at a far distance. So these two stations, unless they are time synchronized, so with GPS time sync. So what is the acceptable deviation that we can take, like to achieve the proper, I mean, study? Because without that, there will be definitely certain GPS time accuracy also which is involved. So how we have considered that particular thing?
Yeah, actually, this was exactly because, as I said, this study was along very, in fact, around more than a decade actually. But we had followed the IEEE standard actually, the protocol. So there the tolerance limit for the time synchronization. So, but we have tested this part. But I cannot say exactly. I don't remember how much percentage of the error that we looked into, and then we refer to whether we have the time synchronization of the signals that we obtained from the two different locations. That I cannot say what was that tolerance limit at the moment, actually. But in our study, but we have considered as per the IEEE protocol for the time synchronization. That I remember. That I think I have also included in my presentation also. This is the IEEE standard of the protocol that we have adopted actually.
Okay, sir. Thank you.
Yeah. This is what but exactly I don't remember. I what was the because it was like how much percentage, because you are your question is about how much percentage error actually that we have included, but I don't remember exactly this at the moment.
Good morning. Good morning, sir. Hello.
Yeah. Yes. Yes.
Good morning, sir. I am Sagar Swarab Sahu. So it was a nice presentation. Thank you, sir. I just want to ask you, sir, how we can use wide area damping control by using BMU signals?
How we can use.
Wide area damping control by using BMU signals.
Okay. Okay. Actually, there are several publications actually, you can say. But again, the point is because this if you want to implement the damping controller in real time, so still there are challenges actually. Now it's because as of now we have the real time monitoring. So it means that uh, whatever the processing delay that we have from the real-time signals, and then we have the detection of the onset of the oscillations, and then we apply the damping controller. So with that case, actually, there are some testing. There are some study that have implemented in the or demonstrated, and then also they make a claim that they have the real-time damping controller design. There had been, but it has been just for a limited grid system actually. So there had been demonstration actually as such. But for again, as I said, to implement in the real time damping controller, you have to get the data from the PDC. Then again, all the pre-processing of the data that you get from the PDC that is involved. And again, there is a delay actually. So that delay has to be compensated somewhere. And then again, because you will apply the damping controller on detecting what is the mode of oscillation actually. So in that case, again, there is further delay involved in the processing of what is the mode of oscillation. And then according to the mode of oscillation, you have to apply the damping controller because all the gains of the controller, actually, that had to be in accordance to what is the mode of oscillation present in the signal. Unless we already know what is the mode of oscillation, that's a different part, actually. But then again, it's like to implement them in real time. This is still further challenge, actually, that, okay, whether the mode of oscillation that is just in this instant of time, it is zero point 0.3 hertz, and corresponding to that, you apply the, have the gain selection, and then feed it back, feedback to the generator, and then again to decide which generator it has to be fed, actually, so that the oscillations damp out. So, or otherwise, there is some other mode of oscillations, and then again, how we select the gain accordingly, and then to compensate the damping, and then to which generator apply. But this is in real time implementation, as a in the lab platform, it had been there are some researchers have claimed over it, actually. But in real time, in the grid, actually, in the actual grid, I am still people are working on it, actually, I can say.
Thank you, sir. It was nice interacting with you.
Thank you.
Thank you, sir. We extend our sincere gratitude to Professor Dr. Nankeshwar sir for that illuminating presentation and to Dr. Prakash Kumar Rai sir for his expert moderation. Thank you, sir, for delivering such an insightful and engaging online session. We now proceed to the formal inauguration ceremony. Thank you, sir.
Thank you. So should I log out the meeting?
Yes, sir, you can leave.
Okay. Thank you. Thank you.
Yes.
Goodbye.